Okay, so I'm going live now. Hi, and good morning to those of you that have attended so far. Thank you for joining. I'm just going to give it another couple of minutes. There's some more people joining as we speak, so if you just bear with me, I'll run the introduction soon. Thank you. Okay, so thank you very much for those of you that have joined this morning. Maybe you've attended some of these webinars that we've been doing on optics at Taylor-Hobson in the past, maybe you haven't, but I'd like to just say a warm welcome to you all again, and thank you for joining. My name's Neil Fitzgibbon. I'm the Optics Business Development Manager at Taylor-Hobson, so I work purely within the Optics Metrology group. Today, I'd like to introduce you to Dr. Mark Vendel. He's a Senior Applications Manager in Optics Metrology at Taylor-Hobson. He's been with the company for just over 6 years, and he has a long wealth of knowledge in metrology before that. So Mark has been working predominantly with the non-contact LUPHOScan range since he joined Taylor-Hobson, and he is one of the foremost leading experts on that. So I'd like to thank him for taking the time to do this webinar this morning. So this morning, the webinar will be taking you through the full lens characterization with the LUPHOScan, which I think you'll all find is really interesting. It's certainly some groundbreaking, stuff in here, and it lends itself to opening up a whole new world of metrology for lenses, and certainly from a fast measurement cycle time. So if you've got any questions, please feel free to ask them, but I only ask that you enter them in the question and answer panel, and Mark or myself will answer those at the end of the session. Okay, so without further ado, I'll just hand you over to Mark. So if you just bear with me a moment to get it started. Okay, so Mark, it's all yours.
Yeah, good morning, everybody. Today we will talk about the full lens characterization with LUPHOScan, as Neil already told you. It's about lens thickness, wedge and Decentre. But first, as Neil said, I'm Senior Application Manager of the Optics Metrology Group. And yeah, if you got any questions, as already said, just type them to the Q&A box and we will answer them afterwards. You can also have a look at the other webinars we already did in the Optical Metrology Group. There are some about the PGI, so the tactile system, but also about the LUPHOScan system, an overview, Fresnel optics, freeform measurements, and the software system alignment. So just have a look at them. They're all quite interesting. Yeah, why are we talking about the full lens characterization? I guess it's quite obvious that there's an increasing measurement requirement everywhere in the world. So for consumer markets like classical cameras, smartphone cameras, AR or VR goggles, the automotive, CCTV and so on, but also in the industries like tool manufacturing for low-cost parts like contact lenses or smartphone camera lenses, endoscopic lenses and so on. But of course also in research, space, defense, and all the other markets that we have. So the precision of the optical systems is growing everywhere. And of course you have to think of a single surface like a mirror, but if you have an optical system, you typically have at least 2 optical surfaces. That's the easiest system, just a lens, your front side and back side. And when you think of an optical system, the mechanical alignment of the system gets important too. So you have to think about the mechanical references, but also about the relation or correlation of top and back surface, if there's a wedge or Decentre error, and the lens thickness. And that's why we are talking about this today. First, I will start with a brief introduction to the non-contact metrology by LUPHOScan systems, just as an overview, and then we will go to the characterization of the mechanical references, as said before, starting with standard lenses, going to molds and toolings, and then we'll come to small lenses like smartphone camera or endoscopic lenses. And then we'll go over to the two optical surface characterization, going back from small lenses to standard lenses. Yeah, the LUPHOScan system is a very versatile optical metrology solution. So you can measure all kinds of surface types, from steep spheres up to hemispheres, aspheres, convex or concave, special types like gull-wing aspheres. You can measure segmented optics like a D-cut lens, or segmented lens, annular objects. There can be steps like on a Fresnel lens or a spherorefractive. You can also measure freeform surfaces. And the way we are doing this is by a spiral scan over the surface. So the object probe is following the design shape in an equidistant and normal way. And while we are checking this line, the object is rotating by means of an air-bearing spindle, so we get the full surface characterization. Our probe is based on a multi-wavelength interferometer, which enables us to do absolute measurements. And this is important for the things coming in a few minutes. Of course, if you want to do measurements in nanometer scale, you can't just rely on the accuracy of the stages. So we introduced a reference frame to our system with some mirrors attached. And while the object probe is moving over the object, we are tracking the horizontal position of the object probe. We are tracking the vertical position of the object probe. And while we are tilting the object probe to be perpendicular to the surface, we are also tracking the run out of this tilt stage. Yeah, when we do a measurement, of course, we have to enter the design shape. We get a preview of the surface. And for example, now we are measuring the front side of a lens. Here's an example I entered here. And when the measurement is done, we're getting the result. So we get a 3D map, top view, and two profiles, and all the numbers you could use, like PV, power, RMS, and so on. And this is still all for the top side. And you can, of course, also measure the back side, which is, in this case, just a simple flat. And you have all the information, the design of front and back surface, as well as the measured data of front and back surface in one file, in one project file. And you also can put the dimensional information like the mechanical references or the relation of top and bottom surface, the same file. So there's no confusion anymore. It's just one file for everything. Yeah, as already said, a lens can have or always have an optical surface, and there are usually also some mechanical references. Like in this example seen before, we've got a flat surface shown here in red, and when we measure this flat surface, we can calculate a tilt between the flat surface and the optical axis of the A-sphere. And we could also measure this cylinder on the outer diameter, the blue one here, and then we can calculate a decentre of the mechanical reference to the optical axis of the A-sphere. It's also possible to combine these two informations, so the decentre information and the tilt information, and like this we will get an axis of the mechanical references, and we can compare this axis to the optical axis of the A-sphere. And there are some more informations. For example, you can get a number for the flatness of the surface. You can measure the height from this flat to the apex of the lens. You can measure the roundness or cylindricity of this outer diameter. and you get the diameter of the lens. And here's a video showing the full procedure. So you've got the design, got a preview. Here you see a small window with a video of the system where the lens is placed in. And when you click start, the system is approaching the lens. It has some collision detection, checking that there's no crash or something like this. Now the measurement starts, so the lens rotates and the object probe is following the design shape. To save some time, I accelerated the video a little bit by a factor of 10. So now we got the surface measurement. You see the result here. And now we are measuring the flat surface of the reference, the red line you've seen before on the last slide. And we are really measuring the full surface of this flat. And then we can get the tilt, the flatness, and the height. Here you also see a false color map of the deviations. Now the second reference is measured. So from the side, the outer diameter. So we get the Decentre, diameter, and cylindricity, for example. And we can also correlate these two results to get an axis with a tilt and an off-center. And that's the full measurement. So it's fully automated. We've got the surface and also the reference, the flat one on top, the outer diameter on bottom, and all the different numbers I explained before. Of course, you can use this for a standard lens, but you could also use it for tools like this example, a molding tool for an endoscopic or smartphone camera lens. So you can measure the optical surface, you can measure the height and the tilt to a small flat ring on the top here. So you get the apex height and the tilt of the optical surface. But you could also measure the optical axis related to the mechanical axis, which is quite important when you have a molding tool and you put two molding tools together. The tilt and the off-center position of the molding tool is quite important. So to get the full mechanical axis, you've got two options. You could, for example, do several line scans, shown in this example, one line here, one line there. And from these two circular profiles, you can also calculate an axis. Or option B, you can do a full cylinder scan. And from this surface data, from this cylinder data, you can also calculate a mechanical axis. And example number 3. Here the mechanical features, they are also called interlocks, are crucial. So it's very important to know the orientation or position of the optical axis to these interlocks, because these smartphone camera lenses you see here, there are two ways to build a system with these lenses. One is by just putting them together, so by click and place or snap features, or however you want to call it. Or the second way is to put them in a barrel, and either way they are fixed. So there's no degree of freedom to do any adjustment, to correct any misalignment. So it's quite important that the optical axis and the mechanical axis is the same. Especially for these very small lenses, the measurements are getting more difficult. For example, if you think of a lens that it has only 2 millimeters diameter, it's possible that the interlocks have a width of only 10 or 20 microns. And additionally, the slopes of the interlocks, typically they are flat interlocks for aligning the tilt, but they are also slanted interlocks up to 70 or 80 degrees to align the off-center position. And they can be convex or concave. So it's quite important that you are also able to measure the concave interlocks up to 80, 85 degrees, or maybe even a bit more. Up to now, I've showed you only the small lenses, so the smartphone lenses, the corresponding molding tools, and the first example had been a lens with only 10 millimeters in diameter. But I guess it's quite obvious that you can use this principle, this technique also for larger samples, and it will be more easy because the interlocks or reference surfaces are larger and easier to access. And we allow for these features up to a diameter of 850 millimeters. So you can use it also for very large samples. Yeah, this had been the mechanical reference. Now we are coming to the optical surface, or the two optical surfaces. Some theory before we start. So if you look at a lens, you've got the two surfaces. And assuming both are A-spheres, you've got two optical axes, one of the side A, one axis of the side B. And with these two axes, you can calculate a wedge error, so the tilt of the two axes. You can calculate a decenter error. Here you have to know where is the decenter defined. We typically define it in the center of the lens, so half of the thickness. So you are independent if you start with a measurement of surface A or if you start with a surface of measurement B. And last but not least, the center thickness is the third number you can measure. But as already said, assuming we have two aspheric surfaces, you can measure all three of these, so wedge, decenter, and thickness. But for example, a very easy example, if you have a flat, so two flat surfaces, you can measure a tilt, so wedge error, but you can't measure an off-center because a flat doesn't have a center point. So it's not a limitation of the metrology system, it's just a mathematical limitation. And here you see a table. So for example, flat surface, you can measure a wedge, but no decenter. For a double-sided A-sphere, you can measure wedge and decenter. And if you got an A-sphere and a spheric surface, what you see quite often, you can either measure the wedge or measure the decenter. It's just mathematically transversion from one to the other. Okay, let's continue with the small lenses. We've seen the smartphone lens a few slides ago. To measure top and back surface, we start with the top surface, doing a standard measurement, spiral scan over the surface. We get the full 3D data, and then we are measuring several circular lines on the back side through the lens. And this is quite a unique feature of our system. So you don't need to move the lens, you don't need to rotate the lens. We're just measuring several circular traces through the lens on the back side. And with these two informations, the optical axis we get from the 3D surface measurement on top and the optical axis we get from the several traces on the back side, we can calculate the wedge and the decenter error. The measurement on the back side is not trivial. It's not only depending on the design of the back surface, but it's also depending on the design of the top surface. It's depending on the thickness of the lens and depending on the refractive index. So if we want to be perpendicular and in the focal plane of our probe on the back side, we have to calculate what is the correct angle to approach the top surface, so it's get refracted to the back side. And also the probe distance is depending on the refractive index and thickness, so the optical path length is changed. Yeah, the advantage of this approach obviously is that we don't need any additional fixture or tooling. You just place the small lens in the system. Can be a pin like this one, just put it on top, do the measurements, and that's it. The measurement routine is fully automated, what we will see in a second. And like this, it's of course a straightforward operation and saving a lot of time. You just click start and the measurement starts with the full surface characterization of the optical surface, the two surface correlation, and also the mechanical references. Here's an example. Here you see a sketch of a drawing of this lens. So first we'll do a measurement of the optical surface that is facing up now. Then we will do an interlock measurement of the screen line here, a flat surface, which will be important for the tilt in the optical system of this lens. And then we'll also measure an interlock that is 80 degrees slanted, the blue lines here, which will be important for the centering of the lens in the optical system. And then last but not least, we will measure through the lens and we'll get the wedge and Decentre error from top to bottom surface. Yeah, here again, a video. We have the design of the top surface and the preview. We are starting the measurement, approaching the surface. Again, there's a kind of collision detection, so we're not crashing into the lens. And then we're doing the measurement. Again, accelerate it a bit. So after the measurement, we get the 3D result. Now we're doing the flat interlock as a first measurement. It takes only 10 seconds to do this. And we get the result here. And now we are at the slanted interlock at an angle of 80 degrees. Again, only 10 seconds. And we got the result for that one too. And as seen in the video before, we get a tilt and an off-center for the mechanical axis compared to the optical axis. And now, as a third step, we are measuring through the lens, measuring the backside. And this also takes only a few seconds. You see the object probe moving from one circular trace to the next one. The process is fully automated. Just click start at the beginning and you get all the results. Yeah, that's it. You get the 5 traces in this case, and you get the result, tilt and off-center of the two spheric surfaces. Okay. Yeah, for standard lenses that are a little bit larger than these smartphone camera endoscopic lenses, we got the issue that the optical path length through the lens would be larger than the working distance of the probe. That means that we can't just measure through the lens for thicker lenses, but we have to measure top and back side separately. And to do so, when you think of just flipping the lens and measure on the back side, you need a coordinate system that is fixed to the lens. And we do this by a reference ring. So we place the lens in an adapter that is mounted to a reference ring. We are first measuring the optical surface of the top side, so we get the optical axis, and then we are measuring the axial and the radial runout of the reference ring to get the position of the reference ring, and then we can combine this information and we know where is the optical surface or the optical axis of the top side related to the reference ring. And then we can flip over the reference ring with a fixed lens. So now the back side is facing up, and we do the same procedure, measuring the back surface, which is facing up now, and again the axial and the radial run out of the reference ring. And like this, we can combine the informations of the top and the back side because the reference ring is known, and we get the relation or the two axes of top and back side. I also got an example for this here. So double-sided A-sphere, it's quite thick, almost 25 millimeters. And here you see the full procedure. You place the lens in an adapter, fix it. Then you place the adapter and the reference ring, mounted by a kinematic mount and fixed by some screws. You put the mount of the reference ring to the system. It's just within hydraulic expansion chuck. Put the ring on top, and then you have the design of the first side. Doing the measurement of the optical surface. And again, the object probe is following the design shape of the optical surface, measuring the full surface. And now, after the optical surface is measured, we are measuring the axial run out of the reference ring. So we get the position, the absolute position and the measurement volume of this ring. And second step, the radial run out. So that's measurement of side A. We get the results and the position of the first side. Manually flip over, enter design of side B, and start the measurement of this one. And it's exactly the same procedure, measuring the optical surface. And after the optical surface, again, the axial run out. And the radial run out, so we know where the reference ring is placed in the system. And then we can combine the two informations of the first measurement and the second measurement, and we get the result wedge, decentre, and thickness. And we can calculate wedge and decentre here because it's a double-sided A-sphere. Okay, so far a summary of what we have seen. So I think everybody agrees that we have increasing requirements on metrology systems because there's a demand in high accuracy lenses and optical systems. So we have to take into account the mechanical references for the alignment in an optical system, but also the two surface correlations, so front and back surface of an optical lens, to get the highest quality of a lens or of an optical system. And yeah, I've showed you a standard measurement of a surface. We measured the mechanical references. I've showed you an example of a mold where we can measure the tilt and the off-center. We've seen a standard lens with two reference surfaces. We've seen a smartphone lens and discussed why it's crucial to measure the references, especially for this type of lens. And we've also seen the two surface correlation where we measured through the lens for small and thin lenses up to a few millimeters, and also for larger lenses with the approach by a reference ring for thicker lenses. So if you got any questions, I'm happy to answer them now. Or if you got them later on, don't hesitate to contact me. Here's my email. Just send me a mail and we can discuss about it. So I will hand over to Neil again and see if there are questions.
Okay. So I'd like to thank you very much, Mark, for that really interesting webinar. I think you guys, those of you that have attended, you'll see that there's some really interesting new metrology and features on there that Dr. Mark took you through. As Mark said, happy to answer any questions going forward. You can contact us via the website. You can contact us via your local applications engineer or local sales engineer. Or, as Mark said, his email address is on there. You can go direct to Mark. So thank you very much again, Mark, for that. Really appreciate that. And hopefully you'll be joining us again in another couple of weeks for another optics webinar. Okay. Thank you very much for your time. See you again soon.
Bye.